Hello my dear students, as you know that I am your science expert, and today in this video we are going to explore the topic that is periodic classification of elements. So let's see that which topics we are going to cover in this chapter. So the topic we'll be covering will be, first we'll start with the introduction, right? Then we'll learn about the Dobereiner law of triad. Then we'll learn about the Newland law of octave. Then we'll move on to the Mendeleev's classification. Then we'll study about modern periodic table, and then we will study about the atomic properties and their variations in different groups and periods. So let's start with the introduction first. So as you all know about the elements, you know that element is a substance which cannot be broken down into more simpler substance. We also did that there are like the elements, they are of different nature, right? For example, we have studied in metals and non-metals that there are certain elements which have tendency of losing electrons, and on the other hand we have certain elements which have tendency of accepting electrons, right? Likewise, we did the physical properties also. There also we saw that there are few metals which are quite lustrous, and on the other hand we have certain elements which are dull in appearance. So likewise, the elements, they have contrasting properties, so it's very difficult to learn about all elements. So if I or you have to study about the elements in a short span of time, do you think that can we do it? No, because every element has something different or special, and it is difficult to conduct study about all the elements at the same time. But do you know that the elements do possess certain common features also? They have certain similarities also, or you can say they have something in common also. So if by any method we could arrange the similar elements together and separate them from the dissimilar ones, then our task would become easy. So the method that can be useful here is classification. That is classification. Do you know that what exactly we mean by classification? Classification means grouping of similar elements together and separating them from the dissimilar ones. So I think that it's clear now that why we are studying this chapter. Just in order to make the study easier and to make you familiar with all the elements and their properties. So that is the reason we classify. So let's look at the definition of classification. Right. So we can define the classification as grouping of similar elements together and separating them from dissimilar ones. Now the way out is clear that if we classify the elements, it would help us to study about the elements. But the task of classifying is not that simple. So different attempts were made by different scientists in order to classify the elements. So let's learn about the discoveries, the discoverers, and also the problems and the limitations of their classification. So let's start with it. So let's start with the Dobereiner law of classification, right? So he is the Dobereiner, right? So he did the first attempt in order to classify the elements. His classification was published in year 1817. Got it? He classified the elements in a tricky way. He arranged the elements in group of 3 and he called that group of 3 as triads. So this is very important feature. Now you must be curious to know that on what basis he would frame his law, that is, he would classify the elements in the triad. So what he did is he arranged the elements in order of increasing atomic masses. So first thing I think is clear that the basis on which he classified was the increasing atomic masses. What he did, he took elements and he arranged them in order of increasing atomic masses, right? And I told you before also that he arranged, like he took 3 elements and arranged them in a group, and that group was called as triad. So within that group, the elements occur in order of increasing atomic masses, and also what he can see is that those elements, they have common properties. They have in general common properties. So let's have a look on the triads. So the first triad is, that is lithium, sodium, potassium. Lithium, sodium and potassium. Right. So the atomic number of lithium is 7, right? And the atomic number for the potassium is 39. So they are arranged in order of increasing atomic masses. So when he did so, coincidentally what happened, that the atomic mass of the middle element was coincidentally equal to the arithmetic mean of the atomic mass of first and third element. So if you have 7, that is the atomic mass for lithium, and you plus 39, that is the atomic mass of potassium, and you take the arithmetic mean, it comes out to be 23. And 23 is the mass of the middle element, that is for the sodium. Got it? So that means increasing atomic masses, and coincidentally what happened, the atomic mass of the middle element was the arithmetic mean of the atomic mass of first and third element. Got it? Now increasing atomic masses, middle element has the atomic mass equal to the atomic mass of first and third, right? And also he could make out that they possess similar properties, like all of them in a group, they are metals. They are typical metals. They are typical metals. And if we talk about their valency, all of them, they possess +1 valency. The valency is +1. And also, when they are added to water, they form their respective hydroxides. So likewise, they have so many more properties which were in common. Right? So he could classify and he could make the triad like this. Let's move on to the another triad. The second triad is this, that is calcium, strontium, barium, right? Ca, Sr and Ba, right? Again, they are in order of increasing atomic mass. The atomic mass for calcium is 40, right? For barium, it is 137, right? And if we take the arithmetic mean of the atomic mass of first and the third element, the atomic mass of the middle element is 88. Got it? So they are arranged in order of increasing atomic masses. Now if we talk about their properties, so all of them are alkaline earth metals. All of them are alkaline earth metals with valency +2. So again, we could see that the properties are quite similar. Right. Likewise, he could make the another triad, that is chlorine, bromine and iodine. Again, they were arranged in order of increasing atomic masses. Again, coincidentally, the middle element possessed the atomic mass equal to the arithmetic mean of the atomic mass of the first and the third element, and all of them have common features, like all of them are halogens. All of them are halogens, that is they are salt forming, right? And their valency is -1, and also their oxides are acidic. Oxides are acidic. So like this, they have few more properties which are in common. So likewise, Dobereiner made the group of 3 elements, that is the triads. But here comes the limitation and the problem faced by him. He failed to arrange all known elements in a manner like that is in a group of 3, that is the triad. So that is the reason he could make only few triads and the classification got failed. So I think it's clear that Dobereiner, like the basis of his classification was increasing atomic mass, similarity in properties and the group of 3, that is the triad existence. But he could not make more triad. So the next attempt was made by Newland. It was made by Newland and the classification was called as Newland Law of Classification. Also, there is a special name given to the law given by him, that is Newland's Law of Octaves. Newland Law of Octaves. Now what do we mean by octave? Oct means 8. Oct means 8. But as we move ahead, I want to share with you that this classification was given in year 1864. And at this time, 62 elements were known. So he just tried to classify those 62 elements. Now he succeeded or he failed, you will come to know later. So let's start with it first. So Newland Law of Octave, like it was given by Newland, that's perfect. Now what forms his basis of classification, right? So again, it was the same feature which he took into consideration, and that was increasing atomic mass. But his classification was quite interesting as it resembled the 7 sur of melody. Like you know that we have 7 surs in the melody or in a musical note, that is sa, re, ga, ma, pa, dha, ni, sa. They are 7 surs. Sa, re, ga, ma, pa, dha, ni, sa. Right. So that means these are 5 and these are 2 and 8th one is again sa and the first one was also sa. So that means first and the eighth sur, it is just the repetition, right? Because sa is getting repeated. So in a similar manner, he said that if you will arrange the elements in order of increasing atomic masses such that, like if the 7 elements are placed in one horizontal row and 8th is placed below the first one, then you could see that every 8th element in this manner shows the repetitive property of the first element. So every 8th element repeats the property of its first element, right? And let's have a look on the classification what he did. So the classification was this, that is, it had hydrogen, lithium, right, beryllium, boron, carbon, nitrogen, oxygen, fluorine. These are 7, right? Then 8 comes below the lithium, that is sodium, magnesium, aluminium, silicon, phosphorus, right? Then we have sulfur, then we have chlorine, then again it is placed below this thing, the sodium, that is potassium and calcium. But like, do you know that his classification on his basis was only till calcium? But do you know that he could classify only till here? He couldn't classify like beyond calcium, because the way he was following, that is the every 8th element shows the same property or resembles its first element, that couldn't be seen beyond calcium. So that is the reason here the lies. That is, he could arrange the elements following his view only till calcium, and beyond that he couldn't do that. So that is the reason the classification failed. Got it? So if somebody asks you about the Newland law of octave, you can say that he arranged the elements in order of increasing atomic masses such that every 8th element repeats the property of its first element. You may get a question like this: suppose if 1 is the first element of Newland classification and 8th is the the 8th element of the Newland classification, so how many elements lie in between them? Right? You don't have to include the first and the 8th one. You have to write that there are 6 elements which are included from any first to any 8th element which is there in the Newland law of classification. So got it. So let's move on to the another attempt. So another attempt was made by the Mendeleev. So it is Mendeleev's classification. This classification was given in year 1869, and I must tell you that this classification, that is the Mendeleev's classification, actually helped a lot in understanding about the elements, that is their properties, their classification. He actually gave rise to a new concept of classifying the elements, that is, he discovered the periodic table. Now what is periodic table? Periodic table is basically like this, that is, it is just a table, right, which comprises of the vertical columns. As you can see that these are vertical columns called as groups, and these are horizontal rows, right, that is called as periods. So you can say that he gave rise to a new sort of concept. His idea was brilliant. So what he did, he tried to classify the elements in a proper manner, and for that he invented this structure, this body, that is the periodic table, that consists of groups and periods. Now the question must be coming into your mind that which property forms the basis of Mendeleev's classification? So that was again increasing atomic mass. Right, but how he communicated to the people around about his classification? He gave the Mendeleev's periodic law. He gave the Mendeleev's periodic law, and according to that law, the statement, let's have a look on the statement first. So according to this law, when elements are arranged in order of increasing atomic masses, right, the elements with similar properties repeats after regular intervals of time. That is, if the elements are arranged in order of increasing atomic masses, we could see the periodicity in properties. That is, the similar property repeats after same interval of time, right? So that this law, it forms the basis of his classification. Periodic table, I already told you that it had groups and it had periods, right? And how many groups and periods were there? In this period, there were 7 periods and 8 groups. Right, 7 periods means 7 horizontal rows, 8 groups means 8 vertical columns. Right, so out of 8 groups, 7 were of the normal elements, and 1 belonged to the transition element. right? So this was the Mendeleev's periodic table. Now, do you have an idea about his biggest achievement? See, the biggest achievement beside the idea of the periodic table was leaving gaps for the undiscovered elements. Right, he was so confident that he even predicted, like as in the periodic table, you could see that there are few gaps left. So he was so confident about its prediction, about its classification, that he even predicted the properties of some undiscovered elements. Right, he thought that when these elements would discover later, they can be placed in a table without disturbing the other elements. So he left gaps, right? And he named those gaps as Eka boron, Eka aluminium, Eka silicon. Eka boron means next to it, Eka aluminium next to it, Eka silicon next to it. And you know that, you will be shocked to know that later those elements got discovered and they filled those gaps, right? So it was the, you can say, a major prediction, right? Now let us talk about the merits of this table and also about the demerits. So let's start with the merits first. He grouped the elements on the basis of atomic mass. That was one of the merit of his table, because atomic mass, he regarded that atomic mass as a fundamental property, and by doing so he could make out the similarity in properties also. Second is, as I told you, his biggest achievement, he left gaps for undiscovered elements, which were actually later filled by the elements, and the elements were gallium, scandium and germanium. So this was the biggest achievement, right? So moving on to the third merit, the another merit was he could predict errors in the atomic weights of certain elements like gold, platinum, etc. He was so confident that while he was arranging the elements, he found that atomic mass of certain element wasn't correctly found. So confidently he neglected those atomic masses and just concentrated on the properties and placed them at the desired place. Now let's look at the demerits. Right, so merits, I think they are clear. First, that was based on the atomic mass. Second, we did that he left gaps. Right, third, we did he made the periodic table. And fourth, he did that he corrected the atomic mass of certain elements. Now let's start with the demerits first. The first demerit is that the position of hydrogen wasn't justified. As you can see in the periodic table, hydrogen is placed among the metals. We know that the hydrogen doesn't possess the properties similar to the metals. It is somehow different. So the position of hydrogen wasn't justified. Second is, wrong order of atomic masses wasn't explained by him. Like, according to him, he had to arrange the elements in order of increasing atomic masses. That means the element with lesser atomic mass should come first and the element with higher atomic mass should come later. But this rule was violated at certain places. Like we can see in case of argon and potassium, we know that the atomic mass of argon is 40 and for potassium it is 39. So as per rule, the first place should be occupied by the element with the lesser atomic mass, that is the potassium, and the next should be argon. But it's not like that. Argon is placed first and then we have potassium. So this kind of rule was seen to be violated at certain places. So these are the demerits, but still I must say that he gave a big contribution in classifying the elements. And later the drawbacks, the limitations of Mendeleev's periodic table was covered by Niels Bohr in modern periodic table, and this is called as long form of periodic table, and we use it, right? Today also we use it and it is universally accepted. So let's start with this classification which is worldwide accepted. And what is that? That is the modern periodic table, or you can say the classification which was done by Niels Bohr. Now, before we go ahead with the Niels Bohr's modern periodic table, I want to tell you one thing. Like we did the Dobereiner classification, we did Newland's Law of Octave, we did this thing, the Mendeleev's periodic table. All these classifications were based on where the elements were arranged in order of increasing atomic masses. They found the atomic mass as more reliable property. That is the reason they classified the elements in order of increasing atomic mass. But in year 1914, there was a scientist, that is Henry Moseley. He performed some X-ray spectra studies and concluded that, like, if we compare the atomic mass and the atomic number, so out of the two, the atomic number is more reliable, right? So that is the reason Niels Bohr framed his classification on the basis of increasing atomic number, not on the basis of increasing atomic mass, right? So if we look at the modern periodic table, so first thing I think it's clear by looking at the table that he also classified the elements in a tabular form. That is, he made use of Mendeleev's periodic table, right? So, but the table wasn't similar to the Mendeleev's periodic table. It was given a new shape, right? But it had the same concept, that is the vertical groups, and it had the horizontal rows. So that means if we talk about the number of groups and the periods, so it had 18 groups. As you can see that there are 18 groups and it had 7 periods. Now let's talk about that, like how he gave his classification. He gave the modern periodic law. As Mendeleev gave the Mendeleev's periodic law, in a similar manner, Niels Bohr gave his classification in a format by stating a law, that is modern periodic law. According to this law, it was that when elements are arranged in order of increasing atomic numbers, not atomic masses, right? If the elements are arranged in order of increasing atomic numbers, right, we could see the periodicity in electronic configuration. That leads to the periodicity in the properties. Got it? So according to him, when he tried to classify the elements in order of increasing atomic number, he could see the periodicity in the electronic configuration, and that gave rise to the periodicity in the properties. So it made the classification easier and it forms the basis of classification. Now let's study about the modern periodic table. So it is the modern periodic table. Number of groups and periods, I think they are clear. 18 groups and 7 periods. Now on the extreme left we have metals and on the extreme right we have the non-metals. Now from 3 to 12 they are transition metals, and you can see that 2 horizontal rows are not included in the main body. They are inner transition elements. So metals, non-metals, transition metals and inner transition metals, right? On the extreme right we have this thing, the non-metals I told you. As you can see that there are few elements which are marked. They are metalloids. They are metalloids, that is the elements which resemble metals as well as non-metals. And if I talk about the 18th group, it consists of noble gases. It consists of noble gases, that means the inert gases which have stable electronic configuration. Now, as you can see that the number of elements present in each period varies. So let's discuss about it first. So in first period, we have the 2 elements, right? Now, if I talk about the second period, you can see that we have 8 elements. In the third, again, we have 8 elements. In the fourth period, we have 18 elements. In the fifth period, we have again 18 elements. In the sixth period, we have 32 elements. And in the last period, we have rest of the elements. Got it? Now, on what basis we put the elements in the same group? So, it is based on the valence electron. That is, all the elements which are there in the same group, they possess same valence electron. Like if I talk about the first group, so all the first group elements, they possess 1 as a valence electron. And if I talk about the second group, they possess 2 as a valence electron. So likewise, all group members, they have same valence electron. One more thing I missed, that I told you about inner transition elements, right? But like the inner transition elements, why they are called as inner transition elements? The reason being, they are placed within the transition series, right? But in order to give a proper frame to the main body of periodic table, they are mentioned like in the transition series, but they are placed outside the main body of the periodic table. The first row is called as lanthanides and the other row which is placed below, it is called as actinides. So the atomic number of lanthanides starts from 57 to 71 and the atomic number for actinides, it starts from 89 and lasts till 103. So I think you got it. Like we have left hand side, that is metals, right side we have non-metals, right? And one more thing, like group 1 and 2 and group 13 to this thing 17, they are called as normal elements, or we can call them as representative elements. Transition elements, I already told you, that is from group 3 to 12, and the inner transition series we have already discussed, that is 57 to 71 lanthanides, and 89 to 103 we have actinides. So I think you got it, and you know about the that is the similarity that exists by the group members, that is they possess the same valence electron. So if I talk about any group out of it, like if I say group 17, right? So the valence electrons of group 17 is 7. All the members, that is fluorine, chlorine, bromine, iodine, they possess 7 as valence electron. And if I talk about group 18, helium, neon, argon, krypton, xenon, so they all possess 8 as a valence electron. So if we talk about any group, all the group members, they possess same number of valence electron. Got it? So that means this periodic table is merely based on the similarity in electronic configuration, right? That means all those which possess the same number of valence electrons, they are placed in the same group, and the one which possess the different valence electrons, they are separated from the other one. So if I talk about hydrogen, we all know that hydrogen is placed in group 1, as you can see here. So hydrogen doesn't resemble the members of the same group because all of them are metals except hydrogen. But hydrogen is exceptionally placed here because this periodic table is based on the atomic number and it takes into account the valence electrons, right? So that is the reason the hydrogen, which has one atomic number and one valence electrons, is placed in the group 1. So hydrogen is exceptionally placed in this modern periodic table. Now let us discuss one interesting topic. Do you know that by knowing the atomic number of any element, we can actually predict the position of that element in the modern periodic table? Let's see how. Suppose if I have the element, let's say we have sodium as an element, right? We know that the symbol for sodium is Na. If I talk about its atomic number, you should know the atomic number. If you need to find the position in the periodic table, you have to be familiar with its atomic number. You should know it first. So that means we know that the atomic number for sodium is 11. Got it? So if I write the electronic configuration, it comes out to be 281. Right? Now we know that like the valence electron is only 1. That means it is placed in group 1. That is clear, right? So it is the member of first group. How we came to know? Just by looking at its valence electron. If the valence electron is 4, so that means it belongs to the 14 group. If it is 3, that means it belongs to the third group. Now, how you come to know about that? See, if the valence electron is 1, 2 or 3, that means if it is 1, it belongs to the first group. If it is 2, it belongs to the second group. But if it is 3, then you need to add 10 to it, right? And that will give its group number. So 3 valence electron, that means we have to add 10. 10 plus 3 comes out to be 13. That means it belongs to 13 group. So it's a kind of trick that you can make use in order to predict the position, right? And why we are adding 10? We are adding 10 because from 3 to 12, we have 10 groups involved in it. So that is the reason we are adding 10 to it, right? So if the valence electron is 1, the group is 1. If the valence electron is 2, the group is 2. If the valence electron is 3, you need to add 10 to it. So it becomes 13. If valence electron is 8, you need to add again 10 to it and it becomes 18. So this is how we come to know about the group of the elements. Now let's talk about the period. So if I talk about the period to which the sodium belongs, as you can see that while we wrote its configuration, it is 281. That is, 2 electrons are there in the K shell and 8 electrons are there in the L shell and 1 electron is there in the M shell. So how many shells it possesses? It possesses 3 shells. So that means it belongs to third period. So third period and first group. It is the exact location where the sodium lies in the modern periodic table. So likewise, you have to be familiar with the atomic number first, then you need to write the configuration, and then by looking at its valence electron you can predict the group, and by looking at the number of shells it possesses. While writing the electronic configuration, you can make out or you can predict about the period to which that element belongs.